recording here. Okay, all right. So we're kind of coming to the end of a small journey for our dynamic memory management stuff. So one part of that is understanding const. So I've tried to think of an analogy that describes const. The best one I can think of is like in terms of coding, it's sort of like someone asking you if you like hot sauce on your food and then sort of handing you this bottle that is way hotter than you realized. So const seems like just a little tiny thing, but when you start sprinkling it on your code, it sort of has this viral effect. And a lot of the big computer science or programming, juggernauts like Google and Facebook that code and Microsoft that code in C++, it's an important part of their style guidelines because it allows them to protect the code. So if you imagine writing, being part of a team that's writing a program of 4 million lines of code, people come and go all the time. They have a job, they write some code, they leave. And so you don't want people writing code that is going to undermine a very, very large program like Chrome or, Microsoft Office or anything like that. So const for programs that are written in C++ is really important for actually protecting certain things. So we're going to go through that today, but we haven't used it a lot in class, and I tend to try to avoid it because it's just another layer that can be very confusing, but it is an important thing to kind of understand. So, quick announcements and some review, but obviously everybody sort of dug in a little bit on Lab 19. That's a really good one. Just give yourself time on that one. Our lab today is optional. It's really pretty small in terms of coding. It's still dealing with our tri-matrix, but it's just injecting it with a little constness. And it's a little bit contrived, I have to admit. It's hard to come up with good examples for const without it becoming a really, really, really complicated situation. So hopefully, after this week, you'll never have to see this triangle matrix class again. But we're kind of, using it every way we can this week. Next Tuesday, of course, is our quiz 5. It does not include today's lecture, so that's a good thing. You don't have to worry about const on quiz 5, but everything else is kind of big on that one. And of course, so is our jigsaw. So with Jigsaw, we'll get, I'm sure we'll have email exchanges, but remember, get your puzzle pieces printing first before you try to create the grid. That's going to, save you a lot of headaches. Because if you can't print out the puzzle pieces one by one, you probably haven't loaded your data correctly, and all things might crash after that point. Okay. So quick reviews. We'll kind of fly through this quickly, but remember that we should kind of have a sense, high level, of these different types of things we can do with our class. We, of course, can write constructors. We can write destructors. We can write a special kind of constructor that is copying another instance of the same class, and we called that a copy constructor last time. And we said, wherever you have to write a copy constructor, most of the code is going to be the same when we are copying from one existing thing to another existing thing. And so we call that the assignment operator, or the overload for the assignment operator. And then we looked at these kind of strange conversion operators for cases where you just want to convert your class into a string or into a floating point value. And in fact, a lot of times C++ is automatically doing that, which can be a little maddening. And we might want to actually even sometimes turn those features off in a particular class. And we will see examples of this one as we get into our shared pointers, which will be coming up after we finish with our puzzle problem. We'll go on to a Facebook homework assignment using shared pointers. So this sort of turning things off idea will come back again to some of our lectures. So now this is really more of a Quizlet thing, but when we see code, we should be getting better at interpreting what it's doing. So that is creating an instance of the f1 variable. It's of type foo. So it's really calling the constructor. Just a normal constructor, and in this case, the default constructor, because we didn't put any parentheses and we didn't pass any arguments into it. Here we are assigning a copy of F1 into F2, which is really the same as that. So we tend to call this, it's not exactly syntactic sugar, but the compiler looks at that and generally says, oh, that's what you mean. So this is a convenience way of expressing that same idea. They're both making a copy of an existing F1 while constructing an F2 or an F3. So that was what we spent some time on Tuesday. We talked about our copy constructor. This does a lot of the same stuff, and Lab 19 asks you to try to implement it, but that's really the overload of the equal sign because F3 already exists and F2 already exists. So we're really destroying the old F3 and replacing it with a copy of F2. So step 4 is probably the hardest part of Lab 19 because you got to kind of delete a thing and then build a thing, okay? So there's a couple ways to do that. Some of you have kind of already tackled that, but that's our assignment operator. This is that weird automatic conversion. Like, how could an integer ever convert itself into a foo? Well, if there's one argument in your constructor, then it can actually do that. Okay, so it sort of depends on how you define foo, but very often we can get away with that. We can force F1 to become something else if foo has a conversion operator for that type. So we saw that as well. So if I ask F1 to become a character, it's going to look inside the class for that conversion operator. Okay. Now that's just a address in memory, right? That is not calling a constructor. So this is like a trick question. It's like, hey, how many constructor calls are happening there? 0, right? That's just saying I will eventually put an address in that variable that refers to some instance somewhere else in memory, okay? So sometimes we're fooled by that and we think, oh, that must be calling the constructor, but it's just a pointer, okay? So now we can use that and say new foo, give me a pointer to that, and now we hook those things together. So there we're calling our default constructor. So a lot of people forget, like, how do I do that? I just want a new instance of foo. Like, do I have to have a variable name? Nope. You can just say, hey, foo, call the constructor without any arguments. Or I could even put parentheses and give it arguments if our constructor supported them, okay? So these are all kinds of variations that we saw in lecture 19. And of course, the last one, calling our destructor. So we should be getting slowly better at recognizing this. The Quizlets are there to help you do that. That's what that's all about. You know, it's kind of a grind to kind of practice those, but hopefully that helps you a bit. And here was that copy constructor all kind of crammed into one line, right? We're not really doing anything. We're just documenting that it's getting called. And the way we trigger that thing is, of course, by kind of having an existing thing and then constructing a new thing based on that, right? Versus that, right? That's not a copy constructor, right? Because both of those exist, okay? So we just got to be familiar with which line of code triggers what aspect inside of our class. Okay. So that's our copy. And then of course the assignment. So I won't take you through all of the guts of that. But basically, if I have something and I have another something and I want to copy F1 over F2, that's going to be our assignment operator, right? So that's what triggers calling of that assignment operator. Or you can think of it as an operator overload for the equal symbol. Okay? So we saw that last time. Of course, well, not of course, we didn't really talk about this too much, but if that kind of, thing annoys you, you can actually say, hey, I want to get rid of that. I don't want to accidentally copy something and have a shallow copy. Sorry, so if I put equals delete after the prototype for a copy constructor, it's basically telling C++, hey, I don't need your help here, right? Don't put an automatic copy constructor in there to do a shallow copy. Get rid of it. Don't have an automatic assignment operator. Get rid of it. So we will see some classes here in a couple weeks that actually do get rid of the default operations for safety reasons because they're like, yeah, we don't want any shallow copies around here. So we're going to get rid of that stuff. So we'll come back to that and see some examples of where those things get used in pretty standard classes that are out there. Okay. So, but these are errors that we would see if we tried to do these things, right? And we had deleted these from our class, the compiler would flag that error and say, hey, sorry, you can't do that, right? We don't support that anymore because that's been deleted. Okay. So that was just a little extra one. We'll see that coming along very soon. Last couple examples here. If I want to return a double, I just overload this way. That's my converter. I say, hey, okay, here's what the magnitude of that complex vector is. Okay. So we saw a little bit of that last time, right? And then I think there may be one more here. So notice here, cout goes to the class and says, hey, what do you got for me? I know how to print a character. I know how to print a double. I know how to print a string. And it goes through the class and it sees, oh, here's a double converter. I'll take that. So it's the cout that's triggering the call to the double. It's looking for anything in the class it can find that it can understand. It just knows it doesn't know how to print this all by itself. So as long as we got a converter in there that cout understands, we will get the result of that, which in this case is just a double value that we return. Okay. Get rid of the scribbles. Okay. So that was our conversion operator. And then these are just our kind of automatic converters. If I got one argument here with an integer and I say n equals 10, C++ is going to try to call my constructor and turn that 10 into a number class and then copy it over the top of that number class. So there's two things going on here. We get our automatic conversion and a copy assignment, right? Or a constructor, copy constructor happens, okay? So a lot going on behind the scenes. Most of the time we just sort of go, hey, that works. I love it. I'll just keep coding, right? I don't know why. It just seems to always create a number for me, okay? But it's only going to happen if I have an argument, one argument in my constructor here, okay? Okay, so all the Quizlets are there if you want to see that stuff. Hopefully it's not too painful, but it's worthwhile. Take the edge off on your final exam as you kind of get a little closer to the end of the semester. Okay, so let's jump into our new stuff for today. And we're going to talk about this thing called an access qualifier. It's kind of a mouthful, but it's just const. It goes before or somewhere near the declaration of a variable. But we can have a lot of things that are constant in code. We can have constant variables. We can have constant pointers that are not changeable. So imagine a compass that never rotates, right? That's kind of a constant pointer. It points to some area that we can go change, but we're not allowed to redirect the pointer. So there's a difference between a constant pointer and a pointer that points to constant data. And we will explore the difference between those two things here today, okay? So there's two kinds of things, const pointers and const data, okay? There is also a different kind of const that happens at compile time. So constants usually happen at runtime, but we can enforce very strict constant status by using this const exp. And so that is a flavor of const that we might run into, okay? And then we'll just look at, what's a good pattern to use if you've got a bunch of things like pi or the gravity. Like, what is the value of gravity that we want to use for doing simulated physics? We want to know exactly what that is, and we don't want it ever changing. So how do we actually implement that in our code? Okay. And then we'll take const to the data class members, right? So constant members of a class, constant member functions or methods. What does that even mean? And what does it mean to have a constant instance of a class? So we'll look at what it means when we start pulling const into our classes. Now, we haven't really talked about static. That's kind of next up on our lecture series, but we'll talk about special variables that are not necessarily just constant, but they may be static. So that's kind of coming next week. But for now, we'll just sort of make a quick reference to it. Next week, we will also talk about something called mutable. Mutable is like a backdoor super powered variable that can be changed even though it's constant, right? So it's mutable, as you can imagine, it's changeable. That's really what that means. So a lot of stuff here, right? And so you kind of go, man, that stuff seems really dry. Why should I care? Well, if you want to see proof, like go to the coding style guide for Google. It's public on GitHub. It's been there for a while, but I think they're probably pretty consistent with it. And they're saying, hey, this is what's important. And you can look up use of const on their webpage and GitHub and kind of go, oh, yeah, they're pretty serious about it. And so C++ is used for a lot of stuff, including, for example, the Python runtime interpreter. So a large amount of the Python programming language is implemented in C++. So it's not like a dead language by any stretch of the imagination. Most of the really highly optimized infrastructure that we code with that's not C++ takes advantage of C++ in some way. So, and these kinds of things like const are for sure part of the style that people use when they write that code. Okay. So let's talk a little bit about vocabulary. Most of us know this, but I will be using this kind of more and more in the next couple weeks. So data members of a class, of course, are just the variables. Some people call them class variables that are inside of our class. When I have an instance of a class, most of the time I have some data members that hold on to data. And as we'll see today, those can be constant or non-constant or something else. Member functions, I like to call them methods, right? Or class methods or class, think of them as functions inside of your class. I tend to call them methods, but other languages refer to them as member functions. And then of course our const qualifier that we're going to use in front of most of these other things, we will see what effect it has on stuff. Static is another keyword. I should have used lowercase here as an actual keyword that changes variables. We'll see one of those today. And mutable, we'll see coming up next week. So these are new keywords and new terminology that we're going to be working with. Okay. We refer to const as an access qualifier. I'll probably just call it a qualifier. One other thing while we're on the subject of vocabulary, aggregate initialization is this, right? So a lot of people are like, what do we call that thing, right? So typically it's referred to as aggregate initialization. Okay, so if you hear me use that term, hopefully you'll know, oh yeah, we've done that a lot of times, but that's what that tends to be referred to, okay? Okay, so let's dive into const. So const, this one page here is sort of the key kind of study notes for most of the stuff that you might encounter, right? It's hard to find all this in one place. But let's take a look at some of the things we can do here. So const int a means a cannot be changed, right? So I've kind of crammed any variable, a couple samples here on one line. You can see they're separated by a semicolon. This one we see a lot, const char star s. So what you're saying is this is a pointer to a character and it is not changeable. So if you have this in your code, that means that you are never allowed to reach inside of this array or these memory elements and change it because you have a constant in front of the data type, okay? And that's what we call const data. You cannot change that data with that S, right? It's not allowed. That didn't always used to exist, but that's been added for about 5-7 years now, okay? Now we can have arguments that once they arrive inside of our function may not be changed. So if I pour a value in there, right, it's going to be treated as constant inside of this function. So I cannot change it, okay? So that's something we've probably seen before. And a slight modification on that is, hey, I know this is a reference, but it's a constant reference, so you can't change that either, okay? So this is just two ways to pass something in indirectly and make sure that no one can change it through that indirect reference. You can't change it via this pointer, and you can't change it via this reference. I should have called this PTR because that's what that is. That's a pointer, but it's a constant pointer. It means you cannot use it to change the data, okay? So this is a weird one. Usually it confuses people. In the beginning, it confused me. It's like, is this a constant function or is it returning a constant integer? And what does it even really mean to return a constant integer? Basically, it is useless. So a lot of people put a const over there and think, ooh, I've protected this function from changing anything, but that is not true. That's really just saying you want a constant return value, okay? So we'll come back to how do you make a constant function here in a second. We could also have inside of our class, apologies for how compressed this is, but this whole thing is a class foo with a private data member A of type int set to 0, and it may never be changed inside of the class again. Const int A is a data member that cannot be changed. And that's okay. We can make data members in a class constant and never changeable. Okay. Couple more. Here we go. Now, here's what it means to make a method so that it cannot make changes inside of the class. If we put the const between the rounded parentheses and the curly braces, which most people don't realize, that now tells the compiler, hey, don't ever let this method change any data members in the class, no matter what. So that means the whole method has been, put in the penalty box. It's like you may not do anything inside that method that changes the class data members. So, but you got to put the const there, not over here, right? It's got to be over on that side. So that is a true const method, right? Here is a topic on pointers, and we're going to dig into all of these, but this is just everything about this lecture on one page. So bear with me here. We're almost there. If I say constant double star D, that means you cannot use D to change anything. We can aim D at something else, but right now we're aiming D at an A. So if I got a little A variable here with a value in it, and then I got a D pointer, I'm saying, hey, you may look, but don't touch the 5 in that box. That's a really terrible D, by the way. I'm sorry, right? So it's like, hey, constant D is looking at the A, but it is not allowed to change the data in the box. So it's kind of a read-only concept. That's a read-only variable pointer, right? I can look at that and read it, but I can't change it by definition, okay? Which is different than saying I can change the data in A, but I can't redirect D to point over here at some variable B. So that's saying, hey, you're not allowed to change the pointer, right? So const pointer versus const data, notice that the const is on the other side of the star, okay? Really subtle stuff here. Don't feel bad if you're like, what were they thinking? But that's how it works, right? So these are things where it kind of doesn't matter where we put the const. As we'll see in a second, I could put the const here or here, here or here, right? Here or here. But when there's a star involved, as soon as you move the const to the other side of the star, you can see I've changed it to purple. Trying to just probably overusing my colors to really point out like, hey, that's a different animal right there, okay? So those are what we call, well, those are relating to pointers, and these are just kind of usual variables and methods. So we're going to dig into these. We're going to do some practice problems on these, but that is kind of the whole lecture on one slide. If you kind of run out of time and you got to come back and just look at this one part of the video or the slides, okay? So, and we'll bring that slide up again in some future lectures as we kind of come back to this stuff. But that hopefully gives you, very, very good orientation. But let's look at these things one at a time, and we'll do some practice, and feel free to jump in, okay? So, of course, when we do something like this, pi should never change, right? So inside of main, once we create that variable, it's locked, and we can never change it again, okay? So probably not a surprise to everyone, okay? But also, I have to give it a value. So if I say const int oops, that is going to be a compiler error because the compiler is not okay not knowing what that value is. Okay. So we got to give it a value. So that's going to trigger an error. Okay. So we can, surprisingly, most people are surprised by this. This is not constant, but I can put it in here to initialize a constant value. So how's that possible? Well, inside of this scope, as the compiler is compiling, it knows what A is by this point. And so it says, well, when I create this thing on the stack, I will give it the value of A because I know I'm going to have the A by the time I create the B. But from that point forward, B is locked. So a lot of people look at that code and say, hey, that's not okay. And it's like, actually, it is. It's okay because B doesn't exist here yet. But once we get to there, we are guaranteed to know what the value of A is. Okay. So the compiler is smart enough to figure that out at runtime. Okay. So we say that is a kind of a runtime const assignment. Okay. Now, as we will see, if we use const expr instead of const, that's a different story. So we'll explore that here in just a couple slides. Okay. So I'll let you look at these if you want, but the beginning of these things, a lot of folks probably know this. So we'll save our time so we can jump into these things on the more complicated slides. Okay. So let's take a look at arguments for a function. So here I'm saying whatever I give you, as soon as you wake up and create this scope, A is now constant. So I could pour a non-const value in there, but it's going to become constant just like on the previous slide as soon as this function wakes up. So if I say, hey, I want you to print A, but I don't want you to change A, probably it would be a good design idea for me to just make that argument const. Because why should this function ever be allowed to modify A? It's a printing function. So probably all of our print me's that we've been doing should kind of be dealing, if it's a function, it should probably have a const value in there, right? So if it's truly a function, not a part of a class, then that would be a smart thing to do. Because then we protect somebody from mucking around with that value in some way that we didn't intend. Okay. Now, many of you are thinking, well, isn't it a local variable? And that's true. So maybe we don't care if you change it inside of your own function. But if it had a ampersand on it, that would be a different story. So const ampersand means we're protecting something that this thing could change. Okay. So that's kind of, pretty standard stuff, okay? So again, const before the type is okay. Const after the type is okay as well. It doesn't change the meaning to move the const over here, which is unfortunately a little confusing. I always try to put it to the outside, but some people like putting it over here. But it does not change the meaning of what we're talking about here. Same with our arguments and our functions. Doesn't change the meaning if we move the const over there, but it's sort of not very standard, okay? So here, this is what we call a const instance. No one is allowed to change F or any of the members of F, even if they're public and changeable. So this is just like a const integer, but it's a const instance of a class, okay? And again, we can move the const over there if we want, okay? Now, as we saw before, this is not very useful. And so moving this over there still means it's not very useful. It just sort of means I'm returning a constant integer value before I assign it to something else. So it's not really very meaningful. So we very rarely would see anything like that. Okay. So the const before or after the type is okay. It's kind of the moral of the story there, if you're curious about that. But I will always put it on the left side. Now, when we get to pointers, things get a little more confusing. So let's take a look at some examples here, and feel free to kind of click into some of the code or try to, do some program IZ coding. But here we have a value A, and then I'm going to lock in a pointer that's pointing to A, okay? So if the const is before the type, is really before the pointer, we call that a constant data. So I cannot change A with D. So if I tried to do something like let's find a violation here. If I tried to say star D equals 7 to try to change this, I'm going to have a compiler error, okay? But this is different. Notice that the const is after the star, okay? So this one, I can change the data, right? I can say star P equals 7, and that's going to put a 7 there. But I cannot change the value of P to point to some other variable. So these are two very different animals here. Const data, const pointer. And it all depends on whether the const is before the star or after the star, okay? Very subtle stuff, but can really be like the hot sauce you pour on your code that starts messing up a lot of things, okay? This is got all your bases covered. This pointer P can no longer be used to change the data, or it can't even be redirected to point to something else, right? So that's kind of a rare animal. People don't do that too much. But basically, the moral of the story is if you're working with pointers, the where you put the const becomes very important, okay? And it all is relative to the star. Is it on the left side of the star or on the right side of the star? Okay. So left side means const data, right side means const pointers. Okay. So we'll have to practice that a little. I always do after I've been away from coding for a little bit. Okay. So I tried to ask ChatGPT to make up a poem. And it did. I said, make up a poem that helps us remember this. And so it said, for fixed data at the start it goes, before the type where clarity flows. Really, really bad stuff. For pointers pointing to the stars, the const comes after reaching far. Yeah. So anyway, bad poetry. Maybe that helps you remember, right? Before, after. Okay. So there's one way to kind of view that thing. Okay. So I tried to do better. And I think this one is actually more memorable. Const after star, leave the pointers where they are. Okay. If you just remember that one, everything else kind of you can figure out, right? If the const is after the star, leave the pointers where they are. I can't change the A, right? The next one was not so good. Star comes later, change the pointer, not the dater. Yeah, I'm not a poetry person for sure. So star in the middle, not the data, nor the pointer, you can fiddle. Yeah, forget all those. Just stick with that one. Anyway, you can tell I was a little bored that day. So let's try to do a little bit of coding with this. See if you can, without using X or Z, change the value. Try to double the value of X without using the X or Z. We'll do the code together on this. And then also copy the data from X into Z, okay? And then print the value finally. So what we're trying to do here, we've got a couple pointers for you to choose from for X and a couple pointers for you to choose from for Z. And we want to do the following. We want to double the X, right, to 20 using one of those two pointers. And then we want to copy it to the Z using one of those two pointers, right? So we want 20 in the box for X using one of those two X pointers. And then we want to double X rather. And then we want to copy it over and then we want to print it, okay? So let's look at how we figure this out because sometimes we just got to get messy with it, okay? So, sorry about that. Let me expand this a little bit. All right. So, so here is our data, right? X and Z. So I got a const double star PTRX and a double star const. Const after star. Interesting. Okay. So that's our two ways of accessing that thing through a pointer. Okay. And then similarly, I have the same two ways of accessing Z. So without using X or Z, let's do our first thing. Double the value of X. Well, normally, if I had a pointer, I could say what's at PTRX star equals 2, right? So, but which one of these X pointers can I use to change the data? Okay, so const after star, leave the pointers where they are. I can't change the pointer, but I can change the data, right? So that means let's try to go with PTR X of 2, right? So we're saying I'm going to choose this one because this one I cannot modify what it's pointing to, but I can certainly change the data. So that should work. Now I want to copy the data from X into Z. So similarly, I want to say star PTR Z something gets what's at PTR X something, right? So I want to read from this address. But turns out I can read from either one of these. They're both readable, right? They're just not similarly changeable. So I'm just going to pick one. And then in order to change the data at Z, once again, I got to go with the pointer that allows me to do that. And that's going to be this const after star guy, okay? And then finally, if I want to print out the Z, print out what is at PTR Z. And again, I'm just going to pick one, but both of them are readable, so they should both work, okay? So Z ends up being 20, which is really what I was after, right? So kind of a really tough example to follow, but we were trying to double the X, copy it into the Z, and then print it out again, just using indirect access, okay? Now, if I had tried to change, once this is all done, if I tried to say, okay, I'm all done now, I'm going to try to change one of these pointers. I got two double values here, right? X and Z. So I want to have this one point at the X now, right? So let's update that or see if we can. PTRZ equals the address of X, okay? So let's see what the compiler says. It says no. Assignment of read-only pointer to PTR2. I'm not allowed to change the pointer, what it's pointing to, only the data that it's pointing to, okay? So that's the moral of the story when we have something that's created with the const after the star. Can change the data that's at the address, but cannot redirect the pointer, okay? Whew, yeah, so that's pretty tough stuff, I know, okay? Just be aware, high level, the location of that const makes all the difference, okay? Pause there for a moment, see if anybody has any questions on that. Okay, all right. I will leave you with that and we will move on. Just a little more summary of this before we kind of leave it entirely. So these are normal things on the left that we have used, many times, right? Standard pointer stuff. I got a PTRA that I'm going to hook up with the address of value 1. Now they're connected, okay? So it's pointing to that one there. And I can replace the value of PTRA with 6. So the 6 goes up there in value 1, okay? And then here's our more complicated scenario. Constant value. So C underscore is often used as a reminder in variable names to say, hey, this is a constant variable. So if you see C underscore in some code on the internet, that's usually a sign that somebody has made that a constant variable, okay? So here are some two constant variables, and then I got a pointer. But watch what happens here. This is the hot sauce. So if you make your variables constant and you say, oh, I'll just take the address of that, the compiler sort of throws up his hands and says, these are not the same things. An integer is not the same as a constant integer. So we cannot say int star ptrb equals a constant because that's a different kind of pointer. And you might think, seriously, C++, like it's just an integer for goodness sakes, right? It's still a 64-bit pointer, but C++ will not allow us to mix constant pointers with non-constant pointers, okay? So we need to have this, C underscore PTRC, which is of constant type. So now we have constant star, so we can say C underscore PTRC equals ampersand or get the address of value 2, okay? It can make you crazy. Once you sprinkle a little hot sauce on a variable, it ripples through so much of your code when you're working with pointers, because it means that all of your pointer variables now need to get const. And so when you start incorporating const variables, you usually do it very carefully and with a lot of sort of planning out, right? Because it can take over the rest of your code, okay? So that's kind of the moral of the story there, is that it's important and very precise, but it can have wide sweeping ramifications for the rest of your code, okay? And so here's just a visual depiction of that, right? I can connect these two together, no problem, right? That's fine. If I try to connect these two together, the compiler is going to be like, yep, nope, these are not the same. This is a const int and this is a non-constant pointer. Okay, so that's not going to work. We got to have that kind of thing down there, and now we can connect those things together. Okay.
Can you draw a vector of constants or something?
Yes.
Like
yes.
without the vector being like stay in place.
Yes, you can have an array or a vector of constant things. And the array or vector can be like fungible, like you can make it bigger, smaller kind of thing.
Yeah. You can still like shuffle them or something.
Yes.
Even though it's const.
Yes, if the array itself or the vector is not const. Yeah, this is a good question because the data type inside of it is const, but if it was a const pointer, that would be a different story versus a constant data. Yeah. 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 So very, very precise. We got to just be careful to basically, like always in C++, apples and apples versus apples and bananas, right? That gets us into trouble. Okay. So here we can redirect C to point it to something else. This is const data, but we can point this at some other const value, right? We're not changing the 10 or the 20. We're just changing what the pointer is pointing to, okay? So think of it as a railroad track switcher. I can have constant PTRC. You're not allowed to change the 20 with this pointer, but I can aim this thing anywhere I have a constant thing over there, right? So this is valid and this is valid up there, okay? Tricky stuff, which is why I don't introduce const in my beginning classes, so because it just gets crazy really, really fast, okay? So now if I move the const to the other side, we got the other problem. Here, we have locked this pointer pointing at value 1. That's okay. So that's actually okay. You might be, wait, this isn't a const value. But it's not the value that we're making const, it's the pointer. So we're saying you can change this data, you just can't change this pointer, okay? So that works, okay? So now I can say PTRA gets 6. That actually works, right? And you might think, wait, it's const. Well, it's just not, I can't bend that pointer to point to some other variable, okay? So here's where we get a mix and match problem, right? These are not the same type. Int star const is not the same as const int, okay? I don't want to drive people crazy. I just want to introduce the problem. Yeah, this is a non-bendable pointer pointing to data that could be changed, but this data cannot be changed because it's const. So therefore, these things are incompatible, okay? Now, if I do a double const, I can do that, right? So that can point to that, okay? It's kind of maddening, you know? So again, moral of the story, use const, but use it sparingly and with good design intention, right? And be aware that it has a different role with pointers before or after the star, okay? Okay. So quick questions. Is this changeable? Yes, right? We can change a value. Can I change that? Sure, that's changeable. I can assign that something. We do that all the time. Is this thing changeable? What aspect of PTRB is changeable? Constant data. So I cannot change this, but I can redirect this to point it at some other variable. That's perfectly fine. So only the pointer is changeable, not the data. Okay. And then here is that silly rhyme, const after star, leave the pointers where they are. So we cannot redirect PTRC to something, but we can change the data at the location it's pointing to. Okay. And of course, we can go there and change that to a 10, right? And a double const, can't do anything with that, right? Nothing can be changed. Okay. So this stuff is tricky. It's tricky. So review the Quizlets, maybe try a little programming. It's not a big part of this class for you to be an expert in this, but if you came out of this class and someone said, what, you took an advanced C++ class and you never learned how to use const, people might raise some eyebrows. So you want to be familiar with this stuff, but it's kind of in the ninja category. It's very, really understanding these things is not something that people do every day. Okay. So I won't take you through the rest of these, but you should review these, maybe try a little code. It's good to, make errors in code to help reaffirm what's happening in code here. Okay. But it is tricky. It is tricky. I often get sort of thrown by it. Okay. All right, so that's kind of just dealing with regular pointers and integer values, regular pointers and sorry, regular variables. So let's just briefly see what this const expr thing is. So const expr says, hey, this thing needs to be known at compile time. We can't wait around for users to input data. So sometimes we use const expr when we really, really, really want to lock something down. So here's an example of what we're talking about. If I ask a user for the temperature and we load it into the temperature, and then I say, okay, I'm going to lock that in now as the high temp. Okay, now high temp can no longer be changed, but we were able to wait around for the user to give us the data before we actually did that. So that's typically what we do. But we could be a little bit more rigorous about it and say, hey, I'm going to get some user input here. So this is what we just saw, right? Here's the regular const. But I could say double exp gravity instead of that, right? So instead of doing this, I could have done this down here. And now the compiler is going to throw an error and say, hey, sorry, I locked that thing down at compile time, and you're not allowed to change its value using user variable. So the const expr just adds some extra cement, right, at compile time. It prevents those changes from happening. We don't do that very often, but it explains why we can get away with this very often. Create a const with something that is waiting around at runtime. This is a runtime const. This is a compile time const, okay? And it's a good way to force us to think about the difference between those two things, okay? Compile time and runtime. Okay, what about just good old constants we want to put in a .h file? So I've had this happen a lot where I have pi defined as something, or I have gravity defined as something, and I find out that somebody else has pi defined too, right? So by putting things inside of a namespace, which we haven't done a lot of, we give ourselves the ability to pull out specific constant values, for example, that we know that we want. So we could say cout namespace double colon, just like we do when we do our out of class classes. That's our scope resolution modifier. So some namespace double colon, and then what do you want from the menu, right? So if pi was in here, I know I'm getting my pi, not somebody else's pi, okay? Which can happen a lot of times when you're coding. So we could put these in a .h file, or we could just put them at the global scope in our current file if we want to. But if you put all your constants in a .h file, then your whole big program and everybody you work with is working with the same constants, okay? So we might see this happen in sort of larger program development, putting a bunch of constants in a namespace, okay? So keeps us from getting into trouble. So let's take a look at this one together real quick. So we're going to create pi in a namespace. Now in program IZ, it's not in a .h file. So I'm just going to bring it up in the regular program IZ kind of mode here. So let's just do this real quick. It's a pretty simple example. So here's our namespace, right? My const gravity 9.8, right? So if I want to print out the area of a circle, it's going to be, usually it's going to be pi times radius times the radius, right? And I got some quotes in there I got to get rid of. But I want the pi that's coming from here, right? Where's my radius? Oh, there's my double radius. So I want to add pi up here. So I'm going to say const, right? Const double pi equals 3.1415926. I used to know a few more of those digits, right? So now if we run it, we should be okay, although I forgot my namespace, right? So I have to say my const double colon, okay? Right, my const double colon. Let's see if that gets it. Okay, there we go. Okay, so three radius, that's my square inches, okay? So not specifically about consts, but this is a good example of how we might avoid having duplicate constant values, right? The question is, where do you want to put that stuff? It's always hard to know where to put your const. So you can put it all in a .h, right, with our usual include guards, or we could, if we just have a simpler program, we can put it up at the top, okay? But this would not be an unusual thing to do. Collect them all in a myconst.h file, and then just include that, and include it as many times as you want with your include guards that we studied a few weeks back. Okay. Okay, so small example. There's this kind of doing what we just saw in main. Okay. Okay, so coming down to a few extra things. We'll get this done by 7, I'm pretty sure. So let's go back to old style strings before the container strings. So we could just collect a bunch of characters in an array. So that is a normal array, and we're initializing it with this aggregate initialization. And we're initializing every position of the array with these letters. So this is just an array with characters initialized, and the dimension comes 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 for the \0. Actually, it might be 9. I gotta check that. So I can go back and change this, right, to something else. Okay, so this is changeable. There's no const in that, right? But if I do something like this, const char star name equals my name, this is no longer an array. This is our const data pointer that we just studied, okay? So very often when we try to come up with a name in our code and we want to lock it down, we are forced to make it a const char star. And we cannot change that. The compiler will say, hey, that is not okay. That is a const pile of data. All of that data is constant at the end of that pointer. So we're never able to go over there and modify that. Okay, so that's a special animal in C++ that lives in a special area of memory. It's a readable but not writable area of memory. Okay, so it has to be a const char pointer. Okay. Okay, so that's one other kind of character string. So I just wanted to point those two things out. All right, so let's move over to our classes and introduce const over there. Pretty similar to what we saw. So let's say our class needs a constant, right? We want the class itself. Maybe I'm making a cool class called math that knows all about math. And it knows how to do square roots and, areas and who knows what, right? So it needs its own data member for pi. So we want to have a constant data member. So how do we initialize that data member to const, right? If it's const, when is the right time to change its value? There's actually two ways. So we could do it in line like this, right, inside of our class, or we could do it via the constructor initializer list, okay? So surprisingly, we can use the constructor initializer list to modify a const before it gets created in a specific instance of the class. Okay. So we can't do it inside of the curly braces. We can only do it via the constructor initializer. So let's take a look at some examples of this. So here's example one. We set this thing equal to 0, and that's it, right? We say that's an inline const initialization, okay? We could also override it by saying val equals whatever came through the constructor. And you might be saying, hey, wait a minute, that's not really looking const. Well, it is as soon as your constructor is done. And now this was no longer 0, it's whatever got passed into the constructor. That's a really cool trick because it means we've created a specific instance of foo that has a specific constant value passed through the constructor, okay? But we cannot do this, right? We can do that one right there, but this one right here would cause a compiler error, which confuses a lot of folks. It's like, wait, I thought you said we could change it in the constructor. Well, yes, only via the constructor initializer list, not via the body of the constructor. Just like, okay, I'll try to remember that, right? Yes.
So the value or the value in val, would it only be not 0 for that instance? Or is it for any?
It's
constructor?
every time, the way this code is written right here, this will overwrite this every time, every single time. So there's no default value here, for example, saying, if you don't give me something, make it 0, right? So the way this code is written here, this val will always be overwritten by this val. And I should have had, I don't think I have code here for this on this page. Nope, I don't. So I could say, for example, foo, right, like this, and then x parenthesis 10. And now val is going to be set to a constant 10 in this particular instance of the class. And nobody will ever be able to change val in this particular instance of the class because we made it a constant 10. Okay. So it becomes constant once foo is constructed. Okay. Okay. So that's a powerful thing, actually. So let's look at a more real world example. Let's say we want to create a class called letter that we can construct and initialize it to a letter, right? Relatively simple. But we want to complain if somebody tries to give us a number, for example, right? So if you give me a 7, I want my constructor to complain about it, right? So my constructor needs to know what are we considering valid letters, like maybe for a password or something. So we want to give our class a constant data member that no one can ever mess with, but that the constructor can use to kind of protect itself. So we're going to, actually, I guess we're going to just test for vowels, right? So sorry, a little more narrow than that. We're going to test for vowels in whatever letter that we're given. So we're going to give our class a constant data member. It's a set. If you all remember our sets, it's like a key value pair without the value. So just keys. So we'll look at this. It'll jog your memory. We're going to set the vowels in there to upper and lowercase vowels. And our constructor is going to let us know if someone gave us a vowel. Okay. So, but we want to set that member through the constructor. We're going to actually initialize that set through the constructor, and then it's going to be constant. Okay, so let's take a look at that code and see if we can do this together. Okay, so here we'll just go on down to our class. So we want a constant set here. So first off, let's see if we can remember how to do a set, right? Set char, right? Vowels, okay? And I'm just going to kind of leave it there for a moment, okay? So that would be a set. We could say it's a const set, right? And then we could initialize it with our aggregate initializer. And I'm going to kind of cheat here and take these folks here and put them there, and then put single quotes around all of them, okay? Single quote, single quote, single quote, okay? So this is our lookup table to see what it is somebody is initializing us with, okay? Okay, sorry, a little tedious. There it is, okay? So that's const. So someone gives us a letter and we want to say if vowels dot count of letter is greater than 0, then that means it's a vowel, right? So this is how we check to see whether the set has a particular letter. So if that's the case, then we'll do a little cout. Cout. That's a vowel. Okay. Oh, sorry. A little Python sneaking into my typing late in the day. And yeah. Okay. Whoops. Keyboard. And yeah. Okay. I think I got that right. And do I have the set loaded? Yep, I got the set library loaded. So let's see what happens when I actually run this, if I get it right. Okay. Did you mean const? Oops, I got a little typo in there. Const. Okay. Let's see if that gets it. Okay. So I've got some vowels, right? So, and I could probably, say, letter, that's a vowel if I wanted to. Okay. Oh, sorry, I'm in insert mode. Control Z, letter. Okay. So why is this useful? Well, there's a time often that comes where we just need to have something all nicely packaged away inside of our letter. We don't want to have this be a global setting out here, right? We put our constants out here and then we refer to that from inside of the constructor. That's very messy, right? So we want to have everything inside of our constructor, okay? So that's really why we do that. And why constant? Because vowels are never changing, right? We don't want that to be modified at any point in time, okay? So that's just a kind of a nice application. So here's what we just did, right? That one right there. But we could have made it a little more flexible. Let's say vowels do change, or maybe there's vowels in other languages. I don't know. So we could have done it through our constructor initializer list. So note the difference here. So I'm saying, hey, you give me a letter and I am going to kind of use the constructor initializer list in a strange way here. I guess nobody really passed me this. They could have passed it as a second argument, but I'm just showing you another way to modify that value through the constructor initializer list, okay? And it could have been passed as a second argument to our constructor as well, okay? So 2 ways to initialize a const data member, in this case, an entire set, okay? Okay. All right, so const member functions. I think we're making the final turn here. So const member functions cannot make changes, okay? And we saw this on that early slide. We said, if we put the const between the argument list and the curly braces, that is how we define a member function that cannot change anything. Not this way. This is kind of useless. A const void is a return value, right? So I need the const to be over there, okay? And this isn't very helpful either, right? That's just still a const void. We just sort of moved it to the wrong side of the void, okay? So if we want a method to not be allowed to change the data members of the class, make it const. So if this was a print me, that's a perfect example of something that should become const. Print me const, okay? So let's take a look at how that might look, right? So now we're gonna learn about static variables next week, okay? But let's take a look at a couple examples here. So here is a method that is const trying to change this data member here, okay? So this const method is not allowed to change that. So that is not okay, right? Because we've said, hey, you are a member that is or method that is const, okay? Sorry, I got that mixed up. Back up. We are trying to change this one here, okay? So this const method cannot change that one. This one is a normal method changing a static variable. That's okay, okay? And this is a const method printing out read only. That's okay. So we can do that, okay? And that's normally what we would do with a print method, is make it const because we're just printing stuff out. Now we will find next week, we'll learn more about static immutables. There's sort of like little backdoor variables that we can use in special ways. But for the most part, this is the typical use case, right? We don't want a printing method to be mucking around with anything inside of the class, right? That's our goal, okay? So that's a const member function, okay? So let's just try this real quick. Let's try to make the print me const. And then let's modify the number class to allow set member function to change data. So this one's, really pretty straightforward. So let's take a look at the code here real quick. I think we're getting down to it here. Come on. Give it a minute. There we go. Okay. So here's our class. Okay, we have a static population. We're going to learn what this is next week. This is really cool stuff. Static variables are really kind of an interesting animal. But for the moment, think of it as a chalkboard at the factory that keeps track of how many instances we've created today. So we're going to set this value to the argument passed in and keep track on a chalkboard how many things we've created so far, okay? And then I got a print me over here that has no business changing anything. So let's put a const in there, okay? So we're converting the whole method because we don't think it should be changing anything, okay? Now, if I try to run this thing is trying to change a data member, and it is a setter, and setters are meant to change things. So obviously that's not going to work, right? So it says, hey, void member set const, where it's read only. We're not allowed to do that. So we'd have to take away that const on that setter, right, for that thing to work, okay? So now we've got things working okay, okay? So let's take a look at what's going on in main. And we'll come back to these static member initializations, but this is basically how we initialize a static member in a class. So I'm jumping ahead a little bit. We'll come back to this next week. The key point here is that we create some instances, set some values, we can print it out, and we're guaranteed that this is not going to mess around with any of the data members, because that is what the prototype of the class tells us, okay? And then we can print out this, call this print population method to figure out how many things have been created so far. And we'll learn more about the static stuff later on, okay? Okay, but that is a const method inside of a class, okay? Okay. All right, last one, I think, const instances. So if I create a, if I have a, I have a const method, right? Some of this is really strange. Here's me creating an instance of the shape class that no one is allowed to change, right? So square is a constant shape. So if I try to change a public data member of the class, then it's going to give me an error because I'm not allowed to do anything to this square shape right there, okay? But I can call a constant method regardless of what it does. So I'm allowed to call constant methods on constant instances. I know this stuff is really off in the weeds for you guys, but if this is a constant data member, a constant instance, I'm allowed to call that constant up, okay? By virtue of this change right here, okay? So here's a little bigger close-up look. So I have F1 and F2. F1 can be changed, F2 cannot. So F1.val is okay, but F2.val is not okay. Even though val is a public method. So this is probably terribly obvious, but that's what's locking us down over here, okay? Okay, and that is that. So a lot of odds and ends there. Take a look at that early page or the early slide in there. But today's lab, which is optional, is really just about adding some const declarations to your triangle matrix, okay? And I'll let you guys kind of dig into this because I know this is pretty dry so far, but just sort of read through the instructions that are in there. All we're going to do is sort of make m const, right? Make it be a const pointer so it can't be changed. We're not saying the data can't be changed. We're saying the pointer can't be changed, okay? And then some of our row members, like our row count, should be const. We don't want our row count changing after the fact once we create our tri matrix, okay? So I'll leave that with you guys to look. This is all straight out of the code, but see if you can kind of get that one working if you want to pursue it. But otherwise, I'll see you guys on Tuesday, and let me know if you get stuck on anything with Program IZ Pro. Watch out for the server issues. Okay. Talk to you later. Thank you.